Hello, this is Miss Moore, and today during chemistry we're going to start our discussion on stoichiometry. Specifically today we're going to learn how to do mole-to-mole conversions. Today's essential question: given the number of moles of reactant used, how do you calculate the number of moles of products? Make sure you answer this essential question completely as part of your summary. And today make sure you have both your periodic table and your calculators handy. Start with a quick review on chemical reactions. So a chemical reaction involves changing substances, starting with something, ending up with something else. And in a reaction, one or more substances, which we call the reactants, the things we start with, change into one or more new substances known as the products, or the things we end up with, the things we make. And an equation describes a system that rearranges atoms and bonds to make a new substance. So to make this a little bit more clear, a reaction, that's what happens when you put one or more substances together in a reaction dish, or a test tube, or a beaker, in the world, in your body, whatever. The reaction is the actual changing, rearranging of atoms. Versus an equation is what you write down on a piece of paper. It's describing the reaction. You write down the reactants and the products. Okay, now let's talk about stoichiometry. So stoichiometry is a method of chemistry that uses balanced chemical equations to predict a couple things. It can predict the exact amount of a product produced from a certain amount of reactants. So if you know how much reactant you have, you can predict how much product is going to be produced. You could also predict the exact amount of reactants needed to produce a certain amount of product. So if you know how much product you want to end up with, you can calculate how much reactant you need. Truthfully, it can predict a lot more than this. You can also, if you know how much of one reactant you have, you can figure out how much of the other reactant you need. Or if you know how much you made of one product, you can also calculate how much of the other product you made. So stoichiometry is a method of chemistry. It's actually using calculations that uses balanced chemical equations to predict amounts of products and or amounts of reactants. All right, before we actually get to the steps of mole-mole conversions, I'd like to give you a little bit of information here. So the first thing is the stoichiometry map. So a stoichiometry map is used like a map to figure out where you're starting and where you're ending up. A lot of students end up not really liking to use the map, but the truth is, just like a regular map, it keeps you from getting lost. So if you could take a moment to copy down this map. So we have mass known, going to mole known, going to mole unknown, and going to mass unknown. So please copy this map down. All right, and then we have a list here of the conversion factors we'll be using this unit. There are three, sort of. So we have mole-mole ratio, which is the mole known equals the mole unknown. We have got 1 mole of known equals the molar mass of known in grams, and we've seen an equality or a conversion factor similar to this one. And we've got 1 mole unknown equals the molar mass of unknown in grams. All right, and if you will find these conversion factors on your unit conversion table on the bottom in the mole area, but I would also like you to copy these down in your notes so that you have them to refer back to. Okay, finally, how do we do mole-mole conversions? But first, let's review coefficients and see what they have to do with stoichiometry. So, the coefficients in an equation actually show the number of moles of each molecule or element being used or created in a reaction. Remember that coefficients were the big numbers we used in front of a molecule or atom to balance our chemical equation, making sure that we had the same number of atoms on both sides of the equation. And as it turns out, those coefficients actually tell us the number of moles of each atom or molecule being used or created in a reaction. So we have a reaction here, C6H12O6, or glucose, plus 6 O2, 6 oxygens, produces 6 CO2 and 6 H2O. So what that's really telling us, now that we know coefficients tell us the number of moles, what this really says is that for every, when we start with 1 mole of glucose, C6H12O6, and the reason it's 1 mole is because there's no coefficient there. We have 6 moles of O2, and that produces 6 moles of carbon dioxides and 6 moles of water. So from here on out, whenever you see these coefficients, think of there being the invisible unit mole written behind them. Because, again, the coefficients in the equation show the number of moles. So imagine an invisible mole coefficient within each equation. So now that we know that the coefficients are really telling us the moles, the number of moles of each reactant and product, we can use these coefficients to build something called mole ratios. And we can use these mole ratios as equalities. So for example, I can write the statement or the equality, 1 mole of glucose equals 6 moles of carbon dioxide. And that's a true statement, because if we have at least 1 mole of glucose, we can make 6 moles of carbon dioxide. I could also write a statement or an equality like 6 moles of O2 equals 6 moles of H2O. Again, true statement. We could also say that 6 moles of CO2 equals 6 moles of H2O. Also a true statement. For every 6 moles of CO2 produced, we make 6 moles of water. And we could also say that for every 1 mole of glucose used, we use 6 moles of oxygen here and here. Okay, so all these things that I have been writing are known as mole ratios, and they come from the numbers in the balanced equation. So these mole ratios we've been working on can be used as conversion factors to compare amounts of substances. And hopefully you remember conversion factors. We had a few in the mole unit. We had 1 mole equals 6.022 times 10 to the 23rd atoms or molecules. And we had another one, 1 mole equals molar mass in grams. And now we have another one. We use the mole ratios. So to get this conversion factor, we find the coefficients in moles for the 2 atoms or molecules in the question. And where do these coefficients come from again? Well, from the balanced equation. Remember, we use coefficients to balance the equation, and then we can use those coefficients in moles as an equality. And from there, we use the 3-step conversion factor method that we already knew. All right, we're finally here. Steps for completing mole-mole stoichiometry conversions. Please take a moment to highlight this title and make sure you do a really good job on this part of the lecture, the notes, because this is an area you will likely need to go back and refer to. All right, so while we're going through the steps, while we're learning the steps of doing mole-mole stoichiometry conversions, we'll do an example along the way. So our example, please jot this down. How many moles of carbon dioxide, or CO2, would be created from 3 moles of glucose, or C6H12O6? And of course, to be doing mole-mole stoichiometry conversions, we need to have a balanced equation, which is right there. We have C6H12O6 plus 6O2, producing 6 CO2 and 6 H2O. Step 1, rewrite the problem as a math problem and then set up the map. So let's write our math problem. So our question, our X, is how many moles of CO2? And what we know is that we're starting with 3 mole of C6H12O6. So our math problem will look like 3 mole of glucose equals X mole of CO2. All right, so now that we have our math problem, we need to also set up the map. So first of all, let me be completely honest. The map isn't overly important for today's mole-mole conversion problems, because they're pretty easy. However, as the problems get more complicated, a map becomes more important. So why don't we learn how to use the map on an easier problems? All right, so a map in stoichiometry is just like a map in the real world. A map in the real world, you find your own location, you find where you want to get to, and then the map will show you how to get there. Same thing with stoichiometry. So we have 2 pieces of information on our map, well, a lot more, but we have known regions and we have unknown regions. So to fill in the map, we find our known, which is 3 mole C6H12O6. And so the region we're in for the known is in mole known. So I'm going to fill in, we know, 3 mole of glucose, or C6H12O6. And then we have the unknown region. And what our unknown is, or what we're trying to look for, is moles of CO2. So we're basically just going right next door. Blank mole CO2. That's what we're trying to find. So that's how you fill in the map. Not too hard. All right, so the next step is to set up our grid and then write the given, or the known, from step 1 in the math problem. I like to line up my grid with my map. I find it helps me not to get lost so easily. And we write our known, which I'm going to just basically drop right down from there. 3 mole C6H12O6 over 1. And I like to cross out what I've done on the map to keep me from getting lost, so I've completed this box here. Step 3 is to use the conversion factor or equality. So you're going to determine the mole-mole ratio for the reactants and products that you're interested in. And remember that the mole ratio is now going to be your equality, and it's the coefficients from the balanced equation. So now let's find our balanced equation again. So here we have both our balanced equation and our math problem. So from our math problem, we see that we are interested in C6H12O6, which is this guy here, and we are interested in CO2, which is this guy right here. So our equality then is going to be 1 mole C6H12O6, because there's no coefficients here. Remember, we're using the coefficients from the balanced equation to get our equality. Equals 6 mole, remember the invisible mole, CO2. So that is the equality we're going to use. And again, we looked at our math problem to see what atoms or molecules we were interested in, and then we used the coefficients from the balanced equation to come up with our equality. So now we have our conversion factor or our equality. The last thing we do, before solving of course, is to put the conversion factor into the grid, importantly, setting it up so that all the units cancel out. All right, so going back to our problem, and then down below I have the equality. We need to put the equality into the grid. One problem is we see that we have moles on the top, which means we need moles on the bottom. However, everything's moles. So we must need to look at something else. Well, this guy is moles C6H12O6, and this is moles C6H12O6. So that is what we need to put on the bottom. Which means that our 6 moles CO2 then goes at the top. And from there, let's check our units. This is important. Please take the time to cross out your units. Mole C6H12O6 indeed crosses out mole C6H12O6. And then let's double check. We're at mole CO2, which is where we wanted to be. Our map tells us we're not lost. So now all we have to do is multiply across the top, multiply across the bottom, and divide. So multiplying across the top, we end up with 3 times 6 mole CO2, which is 18 mole CO2. And multiplying across the bottom is 1 times 1. So 18 divided by 1, final answer, 18 mole CO2. So hopefully you didn't think that was too bad. Okay, let's try another practice problem. In fact, if you think you can do it, hit pause, try to do it without me. Or do a little step at a time, then hit play. Just try your best to do it without me. Okay, so question. Our example is, using the equation below, how many moles of oxygen are required to react completely with 22.34 moles of aluminum metal? So step 1 is to write our math problem and fill out the grid. So our math problem, I know about moles of aluminum, and I'm trying to find out the moles of oxygen. So I will have a math problem of 22.34 mole of aluminum equals X mole of oxygen. Remember, oxygen is diatomic. Now we need to fill in our map. So our known here is in the mole area. So what do I know? I know 22.34 mole Al. And what am I trying to find out? My unknown is mole again. So blank mole O2. All right, so the next step is to set up our grid, and I'm again going to arrange my grid or align my grid with my map to help me keep a little bit more on track. And I'm going to start by writing my known over 1. So basically I'm going to take what's in this first box here and just write it right down there. So I'll have 22.34 mole aluminum over 1. So I've successfully completed that box. And now I want to go from the mole known to the mole unknown. To do that, I need to use the mole-mole ratio from the balanced equation. So going to my math problem, I know about mole Al, which is right here. 4 mole Al. 4 mole, let's write that a little bit neater. 4 mole aluminum. And I'm trying to find out about oxygen. So I go to my balanced equation, and I see that that equals 3 moles of oxygen. Okay, Now we have our equality. And one more time, this equality here came from looking at the coefficients in the balanced equation. Okay, we looked at our question or our math problem to figure out what atoms or elements we were interested in, but the actual equality came from the coefficients in the balanced equation. All right, so what we need to do now is figure out what from the equality goes into our grid. So we're going to look here. We have mole OL here, AL here, so we need to have mole AL on the bottom. So let's do that. So we'll put this guy here, and that means that mole O2 must go on the top. So let's do that. And let's double check. Does mole AL cross out mole AL? It does. So what we do now, multiply across the top, multiply across the bottom, and divide. So now we simply multiply across the top. So 22.34 times 3 mole O2, giving us 67.02 mole O2. Multiplying across the bottom, which is 1 times 4, giving us 4. Now divide 67.02 divided by 4, and that gave me 16.755 mole O2. And that answer is fine, but you might want to round it, and you can round so that there are 2 digits after the decimal, which would give us 16.76 mole O2. There you go. It's not that hard. Just got to be careful, neat, all that kind of stuff. All right, that's it for today. Have a good one.